Start. Now, you're being irresponsible because you're not fixing my mistakes. I'm gonna be like, you know Cemoja? When you make a mistake in his class, he's gonna fix when he makes a mistake in the class, he's gonna fix the mistake and he's gonna blame the students for not realizing it. And I'm gonna do the same. This is wrong. This little arrow. We don't want the other direction, because if the other direction held, we would, in order for something to be in the intersection of x, any set containing that should be in x, but we don't want that. We only want this direction, okay? So fix that. Anyway, let's go back to where we left off. So how can we prove that? How can we prove that this guy is a set? If it is so, let's pretend that this is a set. How can we prove that? We need another axiom, but let's focus on this part. If it is so, is this a set all the time? The answer turns out to be no. And this is going to be an exercise. Where's my red chalk? This is not difficult, but in a sense it's conceptually non-trivial. Show that every set belongs to the intersection of the empty set. So this is a class. It's not necessarily a set. I claim that if you let x to be the empty set, this class is everything. And here's the reason. You can actually see it over here. If you let x be the empty set, is the statement ever true? No. If you have a statement of the form P implies Q, if P is false, what can you tell me about the statement? It's always true. So this is, all sets belong to this class. So the whole universe of sets equals the intersection of empty sets. And we're going to see that this is not a set. So this is not always a set. But if x is non-empty, this will be a set. Okay? In order to be able to prove that, we're going to need another axiom. Okay, you. I don't know your name. That's okay. There was a little mistake over here. We fixed that. Okay? Just so you know. Anyway, axiom 5. Now this is an important axiom. Axiom of separation. Before I explain this axiom, let's again talk about classes. Now, people thought that, like, before all this was developed, people thought that, like, sets are supposed to be collections of objects. So if I collect some objects together, this should be a set. No, we just saw that Russell's class is not a set. Indeed, it was Russell's discovery that not everything of this form is a set. People thought that things of this form should be sets, and the answer is no, they're not. However, in mathematics, we use sets of this form a lot. So we should find a common ground. We know for a fact that not everything of this form is a set. However, we use this kind of definition a lot. For example, you take natural numbers and you say that I'm going to take all the natural numbers whose square is divisible by 3. Okay? You say things like this. You want to collect certain sets satisfying a certain property. Now, this axiom will tell us that we can do this as long as you don't choose all the sets satisfying a property, but you choose these sets from some other set. So it will be the case that whenever you have a collection of this form, this is not necessarily a set, but if x belongs to some set, then this collection will be a set. Okay? And that's exactly the axiom of separation. Okay? Now, the statement of this will be tricky. Let phi z3 be a formula in the language of set theory, obviously, with two free variables, z and p. Now, for any set p and x, there exists a set y that consists of elements of x satisfying the property. Okay, now I have to explain what this is. Phi dot p. Let me write down the formal statement. Again, I'm just writing down the formal statement just so you know that all these can be done within that axiomatic system I described at the beginning, but I mean, English is fine. We can work in English. This is just, I'm just trying to be convincing that all the stuff I write down can be formally written down in some axiomatic system. Okay. To avoid such mistakes, I'm now using my notes. Now, forget about this formal statement. Let me tell you what this axiom says. Let's create a little box here. There is a set P. The reason I call it P is it's supposed to represent the parameters, just like those guys. P is a parameter. X is some set. You give me some parameters, I don't really care what they are, you give me a set X. This axiom says if you look at the class of all sets satisfying the following, these sets come from X. I'm not taking all the sets everywhere satisfying blah blah property, they should come from X. And they satisfy this formula together with the parameter. So this is a formula with two free variables. I'm fixing a parameter P. When you fix a parameter P, think of this as now a property of sets. Think of this as a formula with one free variable. It's not really a formula with one free variable, but you fix this. So the only variable is this first guy. So this is a property of sets. When you plug in a single set here, it either holds or it does not. So this is a property of sets. What this axiom says is the following. The collection of all sets which are members of X and which satisfy this property forms the set itself. So I know that in general, classes of this form are not really, they're not always sets. They're sometimes sets. Like Russell's class is not a set. However, classes of this form are sets. Let me state this in another way. The subset of a set consisting of elements satisfying a certain property is a set. And this is why you can do things like, let's pretend that X is natural numbers. You form the set of all natural numbers that are divisible by 7. This is why you can do it. You say that I'm taking all natural numbers, they're divisible by 7, blah, blah. This is used a lot in mathematics, okay? This is a very important axiom, axiom of separation. Now, I said the axiom of separation, I said this is an important axiom. Unfortunately, I'm lying. You see, let's read this statement. Let phi be a formula with blah, blah. How many formulas are there like that? Infinitely many. So this is not really an axiom. This is actually an axiom scheme. Do you know what this word means? Scheme as in schema. Think of this as a scheme. This axiom is not a single axiom. It consists of infinitely many different axioms. I'm just giving you a scheme to create an axiom. For each formula, this is an axiom. So I have just introduced infinitely many axioms at the same time, okay? Now, if we were working in higher order logics, there was a way to get around this, but in first order logic, we have to do it like this. We just introduced infinitely many axioms because for every property, I want this to be an axiom. I want this to be true, okay? So in reality, this is not a single axiom. This is why I said on Tuesday, ZFC is not really 10 axioms, but infinitely many axioms. We have infinitely many axioms over there. Now, we did that, we did that. Oh, now let's prove the following. Note that it follows from axiom number 5, yes, that if X is non-empty, then the intersection of X is a set. Why is this true? Let me explain this. I don't want to state this as a theorem because it's not really that important. Let X be non-empty. Okay, what property does a non-empty set have? It has a member. Let me name this A. Let B be a member of A. And phi Z be the formula ZA be the formula for every Y well, do I want this? Yes. If it's an A, it is Z is in Y. That's good. Okay. Well, I don't want to write it over here. I'm going to write it down. This is bad. By axiom 5, the class, okay. We're going to use axiom 5. I'm going to create a class. I'm taking all Y such that Y belongs to B. And so I'm choosing my stuff from some set. And I want these Y to satisfy a certain property. And that property is the following. Y should belong to every member of A. Y comes from B, and Y belongs to every member of A. Now, by axiom 5, this class is a set. There exists such a set. This axiom says exactly that this is true. This is my formula, phi YA. This is my parameter. This is my variable. Just apply the axiom. And this is exactly the intersection of A. You can check that. All sets in here belong to every member of A. And every member of A belongs to this class because it satisfies, every member of intersection of A satisfies this formula. It belongs to this class. Okay? So we just introduced the axiom of separation. Sometimes this is called Axiom of Comprehension, I guess. Yeah, sometimes people call it that. So we just introduced this, and with this axiom, we were able to prove that if you have a non-empty set, its intersection is a set. And this is not the only use of this. As I said, we do this a lot in mathematics. We take a set, we take some of its members which satisfy a certain property. Okay? Now, we're going to define more operations on sets. You seem to have a question. No? Okay. But before that, just to get rid of many symbols, just to avoid writing too many symbols, let's make a deal and fix some abbreviations. Okay, from now on, you already know that when I need to write down this, I actually write that. Here's some other abbreviations. I have to do this kind of stuff a lot. I have some formula here, and I said that every member of S, for every member of S, that holds, just like that. Now, this is just too many symbols. Let's abbreviate this. The abbreviation that I'm going to use for this is the following. I'm simply going to write for all x and s, this happens. What this really means is for all x, if x is an s, then this happens. Similarly, I have to write this a lot. I have to say things like, there exists a member of S such that blah blah happens. Well, this is just too many symbols, so here's my abbreviation for this. Formally speaking, these are not allowed in my axiomatic system. They're just abbreviations of these guys, okay? So I'm just going to use this notation from now on. Okay. Definition. Now I'm going to define the union of two sets and the intersection of two sets, which is going to, well, we're going to erase this, don't worry. So the people coming after this class are not going to think that this is like a first year course, okay? Let x and y be sets. We define the union of x and y to be the union of this collection. If x and y are sets, this collection is a set by axiom of pairing. If I have two sets, I can pair them. Axiom of pairing. If I have a set, its union is a set by axiom of union. But what is this? This is the set which contains members of this guy. Members of this guy are exactly members of x and members of y. So the usual union you know is this. Now I'm going to make this bigger so that we can differentiate between these two. And we define the intersection of two sets to be the intersection of that set. Intersection of this set is the set of all guys which belong to all members of this guy. Well, all members of this are simply x and y. So this is the set of all z which belong to z, x and y at the same time, which is that. Okay. We define that to be that to be this. Let's define more sets. I guess you know the difference, set difference. What is this? You all went to high school, come on. What is this? This is the set of all z such that z belongs to x and z does not belong to y. Why is this a set? Why is this collection a set? By axiom of separation. I have some formula, I have some parameter, I have some set. I'm collecting all the elements of this set which satisfy this property. So by axiom of separation, this is a set. The only reason this difference is a set is it's because of the axiom of separation. Now, symmetric difference is defined to be x minus y union y minus x. Why is this a set? Because I just know that this is a set by axiom of union. This is a set by axiom of separation. So you see, I'm actually using all the axioms all the time, okay? Not all the axioms, some of the axioms all the time. So these guys are all sets. Now I'm just introducing notations for them, okay? So each time I need to write, I'm not going to write this every time. This is just too long. I'm just going to write x minus y. So here's an exercise for those who know. Oh, we haven't introduced the axiom of power set, have we? So I can't assign this exercise at the moment. I'll just wait a couple more minutes. Okay. Let me assign 111 exercises. Okay? Show that Z belongs to this intersection if and only if Z belongs to X and Z belongs to Y. Okay. Now, this is obviously true because you know from secondary school that this is true, but you can prove it with this definition. How did I define this? I defined it to be this guy. Well, what is this? This is the set of all Z which belong to every member of this set, but the only members are X and Y, so this will follow. This is conceptually trivial. You just have to, I want you to write it down anyway, because you have to know how to write mathematical proofs down. That's the point of this exercise. You're not supposed to think to do this, except the very basic thinking, which allows you to hold a pen and write things down. Okay. Okay. Terminology. Let's introduce some terminology. Two sets X and Y are said to be disjoint if their intersection is empty. They have no common members. Okay. What else? Oh, a set X is said to be a singleton if it contains a single set inside. That's why it's called singleton. When you say doubleton, it has two elements here. Okay. I'm just introducing some terminology that I'm going to keep using. You have to know what these words mean. You probably already know what these mean, but I have to tell it anyway so that this is a complete course. And those people who are watching this video won't be disappointed by me not telling all these, okay? Anyway, so I promised you earlier that, what am I calling this a lemma? I'm going to call it a theorem. We're going to prove that the whole universe is a proper class. Using the axiom of separation, we can do that. There does not exist a set which contains all sets. There is no set of all sets. Now, I know that this is this contradicts with what you learned in high school. You had this universal set which contained everything. It was a set, it contained everything, possibly itself. And in some set theories, these are allowed. There are set theories where there are universal sets. However, ZFC is not one of them. In ZFC, there is no set containing everything. There is no set of all sets. There's a class of all sets, which we called V. But there's no set of all sets. Here's the proof. Assume not. Assume to the contrary that, well, let me write this down formally first. It is not the case that there exists a set which contains all sets. There exists a set which contains all sets. There does not exist such a set. Assume to the contrary that there exists some set which contain all sets. Then, by axiom of separation, by the way, don't memorize these numbers, okay? I had a student who actually gave reference to the correct number in the exam. There was an exam question. She used the lemma from the notes, and she said by lemma 12 point something. That's going to change if I change the numbering. Okay, don't memorize this like that. You can memorize the names because I actually ask about them. For example, I asked in the past, state the axiom of foundation, state the axiom of union. I asked things like this. You should know the axioms by their names, not by their numbers. No. Okay, then by axiom 5, the following collection should be a set. Well, okay. Let X be such a set. I know that there exists such a set. Maybe there are more than one. I should pick one. Then by axiom 5, the following collection is a set. The collection, the set of all y such that y belongs to x and y does not belong to y, is a set. Why? Well, X is a set. I pick all the elements of X which satisfy a certain property. By axiom of separation, this is a set. However, notice that this is not an arbitrary set. You see, X is the set of all sets. I just assume that it contains everything. So this is unnecessary. Like this statement is true if and only if this statement is true, because X contains everything. I can simply erase this because I assume that X contains everything. Thus, this class actually equals the Russell class I defined at the beginning. This is the same as class of all sets which do not belong to themselves. However, we proved that this is not a set. Contradiction, which contradicts that R is not a set. Okay? Okay. Which part? Do you agree that this collection is a set? Yeah. By axiom of separation. I just take the elements of X which satisfy a certain property. Now, what have I assumed at the beginning? X is the set of all sets, which means that everything belongs to X. So this class is the same as this class. Because this is always true, right? If X is the set of all sets, this is always true. Here's a question. P and Q. If P is always true, this is equivalent to Q, right? If P is always true. That's it. I assume that this is always true. X contains everything. So this is the same as this. But this is exactly Russell's class. Okay? Okay. So there's no set of all sets. So V is a proper class. The universe of sets is a proper class. It's not a set. Contrary to the popular belief, there is no universal set, at least not for this course. I wasn't planning to be this fast, by the way. Am I being too fast? Should I slow down? A little bit, okay. If you don't understand something, just stop me, okay? And someone, like, don't worry about the camera. You can ask, they can ask questions, right? You can ask questions. I just got the permission, so. And if you're worried that, like, if you don't want to be on the video, you can just conceal yourself or write down your question and show it to me. Yes, not the FC axioms. There are other set theories. The whole setup is different. But there are set theories where there's a universal set. They're not it's not ZFC. It's not MBG. It's not Morse-Kelley. Those don't work. Quine's new foundations. I might be making it up. I don't want to make stuff up because we're being recorded. But check out that new foundations. It might contain universal sets. I am not sure. I'm not very knowledgeable about those. But what I'm sure is there are set theories where there's a universal set. Yes.
How is that possible that a set is in the same set or a set is not in itself?
You mean how can a set belong to itself? That's a good question. Actually, okay, axiom 7 or 8, one of the axioms says that a set cannot belong to itself. We will learn the axiom of foundation, which will say that no set belongs to itself. No set belongs to itself. However, at this point, there is nothing preventing that from happening. You see, I just said at the beginning that we have these sets around, and this relation between them either holds or not. It is conceivable that a set belongs to itself. A set is in a relationship with itself. I mean, it's related to itself by this relation. It is completely possible. When we introduce axiom of foundation, this will not be true. This will be impossible. But at this point, there's nothing preventing this. Indeed, there are variations. Like if you ignore the axiom of foundations, there's this Axel's anti-foundation axiom. There are set theories very close to ZFC. You only change one axiom where this is possible. It is possible. It's just a set which contains itself. Like, can you imagine it? Like it's a set. Its only member is itself. It's somehow related to itself. That's it. If you can imagine it, it should be true. In some set theoretic universe, not necessarily ours, we're going to preclude this from happening. This is
now we can have x and x, and we will say that a set cannot be included itself.
Yes, in future we will say that. We haven't said it right now.
Okay, but when we say it,
yes.
We actually say that the Russell class is a set of all sets.
Oh yes. Yes, Russell's class is actually the set of all sets. Sorry, the class of all sets, not set of all sets. At this moment, we don't. In future, we are going to prove this. The whole universe equals Russell's class, but at the moment, we don't know this. When we introduce the axiom of foundation, this will be true.
Okay, but this theorem stays true forever.
This theorem is just true. We don't need foundation axiom for this to be true. Okay, I have 14 minutes. Let me continue. Okay, let me list some basic properties of all the set theoretic operations, because we're going to be using these in proofs. Again, this is 111 stuff. Just so you know, I'm going to finish all the stuff you learned in 111 probably in 2 weeks. So study hard from the beginning, okay? So let's introduce very basic notions like subset, which we haven't talked about up to now. Okay. Let x and y be sets. We shall write this and say x is a subset of y if the following holds. Every member of x is also a member of Y. Okay. We write this if this X is a subset of Y and they're not the same. I'm just introducing more abbreviations, okay? Think of this as me introducing more abbreviations and terminology. In which case, okay, we write this if this happens, in which case X is said to be a proper subset of Y. So a proper subset means a subset which is not equal to the whole thing. And we show it by that notation. Sometimes people simply write this. They only write this C. I don't like that notation because some other mathematicians use it for usual subset. So when I mean proper, when I want to write proper subset, I always write this. Let's continue. The following properties, the following can easily be verified. Now, when you see the phrase, in general in mathematics, when you see the phrase something can be easily done, can be easily verified, that means that I'm assigning this as an exercise, okay? What that means is these are easy to prove. This is like first year stuff, maybe, no, not even second year, first year stuff. You should be able to do it. You should know how to write mathematical proofs. Do it. I'm not going to prove that empty set is a subset of everything. I'm just listing basic properties of these notions. So we have this. This is literally the axiom of extensionality, by the way. If you write it down, you can manipulate axiom of extensionality to get this. And the third property is that the subset relation is transitive. I shouldn't really use that word because we haven't defined it. Now, the intersection of a set is a subset of the union of that set if your set is non-empty. Okay. If you pick some set and an element of that set, that guy is always a superset of the intersection and subset of the union. This is a subset of Y. Maybe I should write this down. Or say Y is a superset of X. This is the dual notion of subset. Subgroup, supergroup, subset, superset is the dual notion of sub-super. Anyway, so if you pick some set and pick an element, the intersection and the union always squeezes that guy. So these are very basic properties. You should just double check that these are true. You don't have to write it. It suffices for you to think about this, like understand why this is true. And that's it. Now we're going to introduce a new axiom called, well, okay, I shouldn't really spoil it. Let's say that, bless you, you are trying to, what are you trying to do? Let me imagine a situation. Okay, let's say that I give you the natural numbers. And you want to do something with subsets of natural numbers. You can pick a certain subset. You can say that I'm picking the subset of natural numbers consisting of numbers which are even. Axiom of separation allows that. What if you want to deal with many different subsets of natural numbers at the same time? What are you going to do? Let's say that you want to talk about the subsets of natural numbers which contain 7. Now, you can prove that there are many sets like this by axiom of separation. But how are you going to collect them all together? There should be a big set which contains all subsets of natural numbers, from which you should choose all these sets which contain 7. The point is, the power set should exist. Now, you know what power set is because you've heard it before. Using the axioms we've introduced so far, you cannot prove that the power set of a set exists. The next axiom will tell us that the power sets exist. Axiom 6. Axiom of power set. For any set X, there exists Y such that the elements of Y are exactly the subsets of X. Exists a set Y. It literally says the power set exists. I'm going to name it power set in a second. I haven't named it yet. Let me write this down more formally. For all X, there exists Y such that for all Z, Z is in Y if and only if Z is a subset of X. Now, I said I'm going to write this down more formally, but I cheated. This symbol is not in my axiomatic system. However, it's an abbreviation for something. I don't want to write that down. It contains too many symbols. So I'm just going to use these abbreviations from now on, okay? For every set X, there exists a set Y whose members are exactly subsets of X. The set Y in the statement is called the power set of X and denoted by this. If you know LaTeX, this is \Metcal. For those who know LaTeX, okay? This is a fancy P. It's a curly P. So the power set exists by this axiom. How many minutes do I have? Not many. 5. Okay, let me assign a simple exercise for those who have taken 116 or 367. Those who did not take these courses can skip these. Show that for any set X, the power set together with the symmetric difference operation is an abelian group. Abelian group in which every element has order 2. So this is a set. This is binary operation on that set. Show that this is an abelian group where every element has order 2. And if you don't know enough algebra, skip this exercise. It's not that important. Show that for any set X, now I have a group. I'm going to add another operation, and this is going to be a ring. This is a commutative ring in which every element equals its square. Over here, okay, when you think of this as a ring, this is my addition, this is my multiplication, okay? So when I say square, I mean you're supposed to use this operation. Now, I'm not assigning this exercise because it's difficult. I'm just assigning it so that you see different examples of rings. Like, have you ever told you that this was a ring? Probably not. Maybe yes. Well, I mean, if you let this to be some giant set, some infinite set, you can get weird rings with special properties. Maybe you need to get things like that, things of that form. For example, if you know, okay, this is for those who know algebra. This is isomorphic to copy of Z2, where you have power set many copies. Sorry. No. X many copies. Okay? This is like a direct product. Anyway, you can show these. Now, I have 2 minutes. Let's go back to this. This is a very powerful axiom. It says that the class of all sets which are subsets of a fixed set, it's a set. Why is this powerful? Later on, we're going to learn about like countable sets and so on. It is the power of this axiom together with the axiom of infinity which allows you to prove that uncountable sets exist. Without this axiom, even if you assume axiom of infinity, even if you assume all the other axioms, without this one, you cannot prove that uncountable sets exist. The higher infinities exist because of this one, okay? Now, we are going to stop here. We basically stopped at the beginning of section 2 from pairs to products. In the next lectures, what we're going to do is we're going to cover relations. We're going to learn what a relation is, what a function is, and we're going to learn types of relations and functions. And this is still stuff from like the old. That stuff will be the stuff that you're familiar with from 111. But when we come to products, you're going to learn the first non-trivial thing you learn in this class. Cartesian products of sets where the product is taken over an arbitrary collection. And then afterwards, we're going to talk about natural numbers and so on. You know the syllabus. So have a nice weekend. I'll see you next week.